Okay. Okay, sorry for the technical problems. Let's just recap where we were. We have now a formula, or at least a formalism, for computing the endpoint correlation function in at least our massive scalar field theory, even if you turn on interactions. So for example, you can add a potential, and as long as it can be expanded in polynomials, which we will assume can be done, then we have a formula. So in particular, the vacuum expectation value of the endpoint function now in the fully, this is in the interacting vacuum, can be written in terms of Feynman diagrams, right? So this is basically the sum of all what I actually prefer to call fully contracted Feynman diagrams. Okay. So for example, let's revisit our Phi-4 theory, just to recap what goes on there. Then we know that the 2-point function, for example, let's do the 2 and the 4-point function. The 2-point function in position space would simply be the following. First you have just the classical, so to speak, Feynman Green function. And then we discover that there is a one-loop correction that involves this guy, right? So there's only one vertex here, so it's easy to figure out what, once you introduce non-linearities, what needs to be contracted with what, right? Some theories are more complicated. So for example, the standard model of particle physics has multiple, many interaction vertices. So it takes a while to get used to what they are. And if you want to do a 2-loop calculation in the standard model, that would be pretty crazy, and so on. So you get next term, you get things like two interaction vertices. You can get, for example, this guy, right? So you have 2 interaction vertices. You can also have, for example, this guy, 1 here and say 1 here. That's also allowed, and so on. It's just basically all the possible contractions that you can write down involving 2 external points, and so on. And then, for example, for the 4-point function, remember there are no there are no odd point functions here, even with non-linearities. So without interactions, we've already noted that Weik's theorem tells us, because you always have to contract the fields in pairs, Weik's theorem tells us that without interactions, all the odd point functions vanish. But in the Phi-4 case, even with interactions, because this interaction is quartic, so it's even in the fields. So when you insert them in the way we do this is we Taylor expand this guy from the exponential and try to figure out all the contractions between them. So if you have odd powers of external fields, you will have to find some way to contract them with the vertices. But this is even, right? So there's no way you can get even powers of fields once you have odd powers of them for external fields. External meaning you're evaluating them at some external point, like x and x prime and so on. So even in this case, at least within perturbation theory, it's not possible to get. Let me just call it 1, 2, 3, 4, just to save myself some writing. So 1, 2, 3, 4, and by that I just mean x1, x2, x3, and x4. And this guy we have seen without interactions. We've already seen 1, 2, 3, 4, and then you have 1, 4, 2, 3. And then you have 1, 3, 2, 4, and then plus, and then now you, so without, if it's just classical, then without interactions, then you're done. But now with interactions, you get an infinite series, just like we do have here. And for example, the first non-linearity, but still kind of semi-classical because you don't have any loops. I'm not sure if I'll have the time to count the powers of h bars, maybe towards the end of the course. So if I have the time, I'll come back to this topic of, so I've been claiming that these guys involve higher quantum corrections. So roughly speaking, you can see this because each contraction involves commutation relations. If you look at the operator formalism, and so in that sense, you can see why there are more H bars. But to do it systematically, I think again the path integral method actually helps here. But so let me see if I will have time, maybe towards the end of this course, to talk a little bit more about that. But for now, you have to take me at my word that the higher loops you go, the more H bars you will get, because this is inherently a quantum process. Heuristically, I think the best way to see it is that if you just try to solve the theory, for example, the solution to this theory, you will never get these kind of Feynman diagrams. Right? If you just try to find the solutions of Phi-4 theory, even within perturbation theory, you will not get this sort of diagrams. That's another indication that these come inherently from the quantum character of what we're doing. Anyway, so let's keep going. So this is still, this you do get in classical theory. So this is sort of semi-classical. And then, depending on whether your lambda has H bar in it, and then now you start getting quantum corrections. For example, you can get a loop like that, right? You can take these guys and stick in a loop, and then now there are many permutations. So I'm not going to write them down. Okay. This guy also can have a loop, for example. Right? You can have a loop on the legs and so on. You can also have, let me see, right, yeah, so, yeah, let me stop here because there are, too many infinite number of diagrams you write down, and so I just want to show you what I mean when I say fully contracted diagrams. Essentially, you have to take your interaction vertices, decide how far in perturbation you want to go, and then you just have to figure out with this 4 vertex, all the possible contractions you can make with the external endpoint space-time locations that you want to compute, and consider all the contractions. What I do want to, so up to now is just recap, right? We even talked about how the vacuum bubbles will cancel and so on. So I won't revisit that. But what we haven't talked about is how the these things look like in momentum space. And this is important because of our, what we're going to do is we're going to next figure out what is the endpoint function good for. And one of the reasons why it is important is because, in fact, it allows us to extract the scattering amplitude. Right? So far we're doing in position space. So we need to do Fourier space endpoint functions. So the 2-point classical one is easy enough to talk about, right? So, but let me just define it in general. So what I mean by that is I want to write down phi of, let's say, k1, phi tilde of k2, all the way to phi tilde of kn. And by this, I'm going to suppress my other dependence. For example, it's still the vacuum, still the fully interacting vacuum. And then I'm even going to drop the time-ordered product symbol. But what I mean, so let me just write it down once, is that this is the integral over the space-time points Fourier transform to k-space. So it's dx1 to the plus ik1 dot x1, and then integral over dx2 to the plus ik2 dot x2 all the way to dxn to the plus ikn dot xn Fourier transform of the fully nonlinear endpoint function. Okay, so this is what I mean when I say this guy. And so let's see what it looks like for these diagrams. And what I'm going to do is I'm going to do it up to the first order in non-linearities here. And here I'm just going to do it to this order. I won't bother with these guys. So the point is the following. Number one, my Feynman propagator, in fact, we know is Fourier representation. So, by the way, this is why you need to know, even if you think you got the answer already, it's sometimes very useful to represent your answer in different forms. This is an example, right? So you can compute this in position space, but in quantum field theory, it's often the momentum space answer that is useful because it allows you to do this sort of Fourier transforms quickly. So there's an I, and then there's a k squared minus m squared plus I epsilon. So I won't do it in class because I think you guys can handle Fourier transforms. But if this is, remember, the non-interacting guy. So in this case, for example, the non-interacting K1, K2, you can discover for yourself, is just actually I over K1 squared minus m squared plus I epsilon. This is a K. And then you have a delta function. And this is a K1 plus K2. Okay, if I write down phi tilde K1, K2 like that, it's a plus. But it gets more complex. So this guy is in fact this guy, as you may remember. So let's do this guy here and see how that works out. this guy, so let's break that down, involves the following. Phi x prime, that's always the external fields. But now I have one power, remember this means that one power of this nonlinearity minus I lambda over 4 factorial. And then I have to integrate over these fields, so let's call it phi z to the 4th power. And remember I have to contract all the possibilities, I have to consider all the possible contractions. But no matter who is contracted with, we know what's going to happen. These fields are going to be replaced with Green's functions. So what we really need to figure out is, after contracting these guys with either themselves or Green's functions, what happens to those? What happens to those Green's functions, right? And so let's, without needing to assume who they are contracted with, this term will become the following. You have g f of z minus x1, g f of x z minus, actually let me do the other way around. X1 minus z doesn't really change the answer, but I just want to stick to my convention in my notes. X2 minus z, gf x 1, 2, 3, and then 4. And what I'm trying to say is that no matter what they are contracted with, these are the locations of the fields they are contracted with, but I always have this z integral remaining. And so let's see what that gives us. Okay, so this means it's an integral over z. And all of these have, as we've seen over there, a Fourier representation. So let me just call it P1 to P4. P1 to P4. And then you have I over P1 squared minus m squared plus I epsilon multiple. You have 4 factors of these guys, P1 to P4. And then what's crucial is we have to remember our exponentials. So these guys, I'll write it out as I P1 dot x1, and then minus P1 dot z. So it's a plus I P1 dot z. And then there's e to the I P2 dot x2, and so on. Let me in fact factor out the z's. P3. Okay, let me write it out then. E to the I P3 dot x3, e to the I P4 dot x4. Okay, and then the z part, let me just add them all up. It's actually P1 plus P2 plus P3 plus P4 dot z. You will always have this term because of the Green's functions. All I've done is replace those Green's functions there with this expression, but collect the terms involving z. Because now I can integrate them over z, and you see that what I will always have is I will always have a delta function. So I think it's time to erase something. Yeah, let me erase one more line and see if I can squeeze it in here. Okay. Maybe I'll erase this little bit here. And just write down block. Okay. Because all I want to know is I want to just do the next term so that you guys can see what happens. Okay. So Yeah.
How about the factor of lambda over factorial?
Yeah. So I haven't I'm just telling you what's happening to the vertex. Okay. So this is just this integral here. I don't care yet about other factors. Right. Yeah. But I will come to that in a little bit. Yeah. So the point here is that now you discover that you will get a delta function 2 pi to the d, and then delta function of p1 plus p2 plus p3 plus p4. Okay. And then you also will get, of course, you still have your remaining momentum integrals p1 to p4. And then you still have your exponentials, sum over L, PL dot XL, and then you still have your product of propagators, right? L prime squared minus M squared plus I epsilon. Okay? But the point here is that as far as the vertex is concerned, there will always be a delta function. Momentum delta function. So the way to think about it is that you have momentum flowing into the vertex P2, P3, P4, because now we're trying to go to Fourier space, and this vertex needs to conserve momentum because the background space-time is translationally invariant, both in time and in space. And so when you go to Fourier space, it's not surprising to see that right, it's not surprising to see that, in fact, we have momentum conservation. And then now we come to your question, right, which is that, of course, we also need to worry about how many possibilities there are to contract with this guy here. So if you just do the classical calculation, you will discover that for this term here, if you're contracting with the external lines, then the 4 factorial will go away, and you will get a minus I lambda only. So in fact, I'll do it very soon, but I want to show you that, for example, what happens here. Right? So if you step through this calculation, you will discover that this term in particular, so this term in particular will look something like this, right? So there is a momentum going in. Let me do it again because I'm doing it in momentum space. So let me call this K. So if I know that momentum is conserved, this has to be K as well. There must be an overall momentum conserving delta function because we know that there is one here as well. Right? Remember that, well, in this case, this becomes, if K is going in, and then K prime is going out, then there's a delta function in K plus K prime. Sorry, let me say that properly. This guy in momentum space, K, and then not going out but going in, K prime, then this will become delta function of, because there are 2 points. Usually we just end up erasing this. Okay, so I over K squared minus M squared plus I epsilon. So formally that's what we're supposed to write down. But after a while you get used to the fact that whenever you see a line there must be a momentum conservation, right? The momentum can't just go somewhere else. So we usually end up just erasing this, even though there are 2 points, and we're Fourier transforming with respect to both, usually we just end up erasing the other guy and say that, well, there's just one momentum, and we just basically ignore the delta function, right? It's kind of implicit. So same thing is going to happen however many orders you go, right? Momentum conservation, because you will hold at every vertex. So even if you insert as many interactions as you want, momentum will continue to be conserved at every point, every vertex, I mean, and therefore overall momentum conservation is always preserved. So again, this guy will have, so let me just drop the overall guy. This will have K, and K must come out. But now there's an additional momentum that flows here. But because it's a loop, what happens is that whatever goes out here must come back. So automatically momentum is conserved. So what will happen here is that in fact, because it's now contracted with itself, instead of with external points, what you'll discover is that here you will have something like a momentum. It's like this actually. So you will have your momentum conserving delta function will only involve the k and k prime actually. So if you have a k and k prime, let's do this. It will give you 2 pi delta of k is coming in, and then it must be equal to k prime. And then this will be I over p squared minus m squared plus I epsilon. But then there will be a p integral, right? So remember, there also a p integral with a momentum conserving delta function. And then there are these external propagators as well, right? So these guys are contracted with some external points. So there are also external propagators, 1 over k squared minus m squared plus I epsilon. And then this guy is another I over k prime squared minus m squared plus I epsilon. Okay. And I've advertised before, once you go to the loop level, you will start to have divergences. So I won't do it here, but if you look at the dimensions of this guy, integral over p, and then there are no exponentials anymore, but because we're all going to Fourier space, this will be I over p dp over p squared. So it's momentum to the d power minus 2. So in 4 dimensions, this will be p. This whole thing will scale like momentum to squared, right? This will go like momentum squared. So this integral most definitely diverges at high large p. Anyway, so I won't go there. I'm not going to try to tell you what to do with it because we just want to, for now, content ourselves with the pre-level, the classical diagrams for now. Right? So I won't go there, but this is to show you what the rules are. Right? There's a momentum conserving delta function. Each line is a propagator, and then there are factors. Of course, I should include my I minus I lambda over 4 factorial. But there are combinatoric factors that I won't bother for now. I just need to figure out how many contractions I have. But what I'm going to do is I'm going to move over here and do these guys, and I'll stop at this point to just show you what happens here. Maybe just a few more words about this. So apart from scattering amplitudes, what the 2-point function, what the endpoint function gives, particularly the 2-point case, is that it can tell you something about the propagation of these particles at the quantum level. So remember, Green's function itself is supposed to tell you, even at the classical level, it's supposed to tell you something about how signals propagate in space and time. There's some issue with causality I mentioned before. The Feynman propagator in particular is actually acausal. Right? It has a retarded part, it has an advanced part, and there's even a part that goes outside the light cone. But however, you can find ways to coax, how the signals propagate out of the Green's function. So what you should think about is that Okay, so yeah, so let's do it. So that's the 2 point. Okay, and again, I'm just showing you what the ingredients are without pinning down the symmetry factors and all the details. Because I want to do this. So for the 2 points, these three actually we already know. Okay, so in particular, for example, let's do this guy here. 1, 2, 3, 4. So let's call this K, and let's call this K1, 2. And let's call this K3, 4. Right? Just to remind us that this came from this. And we already know because that's just this guy here. So all that's going to happen is that I have I over K12 squared minus M squared plus I epsilon. And then I have another factor here, right? It's a multiplication. So it's just I over K3/4 squared minus M squared plus I epsilon. Again, if I ignore this, is ignoring the momentum delta function. But if you insist that I put something there, then there will be, in fact, I'll now have to call the other momentum something, maybe the prime, right? So for example, I might have to end up doing this K12 squared, and then, I'm sorry, K12 not squared, plus K12 prime, for example. But it's understood, right? So once you understand that there are external momentum for each endpoint, basically I can just tell you, okay, the Fourier space might modulo the momentum conserving delta functions of this guy, namely the Fourier transform of the lowest order Feynman-Green's function. So what is non-trivial, what is slightly more non-trivial is this guy. And so this one we should try to pin down a bit more carefully, including the symmetry factors and so on. So let's do that one. It'll turn out that the answer is very simple as well. Okay. So, right, so let's do this one. But now I have 4 external legs, so in principle I need 4 momentum, right? So let's call it K1, K2, K3, K4. And what happens is that, of course, I need my external propagators. Like, so remember that this came from Fourier transforming something like this, phi k, so phi k1, phi k2, k3, k4. But now I have an external, so these are the external fields which I now have transformed to Fourier space. But now I have one interaction vertex, right? So I over 4 factorial lambda, and then integration over the Phi-4 interaction vertex. So I write this down because I need to figure out what is the correct combinatorics factor. So we discover that one of these guys must be contracted with this guy. So there are four ways to do that. And then there are 3 remaining fields which I'm going to contract with this guy. So there are 3. And then there are 2 remaining. And then there's no more choice here. Okay. And this is just to remind us, these guys will give us, remember each contraction gives me a Feynman Green function. But now I'm in momentum space, so it's just going to give me k1 squared minus m squared plus I epsilon times the other guy, k2 squared minus m squared plus I epsilon, and so on. Okay, so these are the contractions. But with the combinatoric factors, there are 4 ways to contract the first guy, 3 ways to contract the second guy, and so on. This is basically 4 factorial, which will exactly cancel out the 4 factorial below. By the way, that's why we define Phi-4 theory with a 4 factorial, because this lowest order interaction will always just cancel out all the factorials will cancel out, and you get minus I lambda up front. But of course, we have to remember what happens here. But what happens here is that now we've taken care of all the contractions already. So what remains, right? All the contractions are basically the Green functions that are discussed over here. Okay. And so because I've taken that into account already, the only remaining thing is this guy here. So there's now a integral, right? There's an integral k1 kn, and then delta function. I need to be a little bit careful. So when I did this, I called this P, but the external momentums are K's, right? So what really is happening is the following. I need to be a little bit careful. Is that there is a delta function that comes from contracting the external point with the vertex. So it's K with the P, and K4 with a P, and K1 with a P, and so on, right? And but then you still have this guy, okay? So what happens is that when you integrate over these guys, let me do it once. Okay, so there's a delta function of say K1 with P1 all the way to delta function of K4 with P4. And then we have an integral P1 with P4. And then you still have this delta function that conserves the overall momentum. P1 plus P2 plus P3 plus P4. So what happens is that you can integrate over them, and it will just go away. This will go away, everybody will go away, and you're left with this expression. So basically the answer is now minus I lambda, and then the product of the external property is I over K L squared minus M squared plus I epsilon L from 1 to 4. Okay. So once you get used to it, then you don't have to worry about these delta functions. You kind of just know that propagators are always going to be these 1 over I over K squared minus M squared. And then every vertex has a momentum conserving delta function. And there's always an overall momentum conserving delta function, which we will neglect. So the only time you'll ever end up having a momentum integral to do is when you have loop integrals like that. Okay, so for example, this guy here, where you will have a momentum you have a momentum integral to do. But for classical diagrams like this, you don't. So So and maybe I should do one more diagram, and then you see what I mean. So yeah. So let's see. Right. So let's do, for example, the 6. Yeah, let's do the 6 because it's easy to do this one. So let's do a 6-point classical diagram like this. 1, 2, like that. So you can think of it as 3 particles scattering, and then they destroy each other, and then it comes out again. And so we know that there's such a process because this is a 4 vertex, and this is 4 vertex, right? And so how do you get this? You must Taylor expand this up to second order. So there must be a 1/2, and then you get a I minus I lambda over 4 factorial squared. Okay, and then you have Z1, Z2, phi Z1 squared to the 4th phi Z2, and then these guys need to be contracted with each other and with the external fields. So the external fields are now phi tilde of K1 all the way to phi tilde of K6. Right, so let me call this K1, K2, K3, this is K4, K5, K6, and then let me call the internal guy, let me call it P. Okay. So you already know by conserving delta momentum P must be equals to K4 plus K5 plus K6. Or it must be equal to the negative of these guys. In other words, P plus K1 plus K2 plus K3 must be 0. Okay. So you already know that's going to happen. So what's going to happen is that right. So what will happen is that you just count the propagators that you have. The only thing you need to figure out is what's the right combinatorics factor. So let's do it, right? So this guy needs to be contracted with one of these guys. Okay, so so there will be four ways. There will be 4 K1, K2, K4, 5, 6. So 4, 5, 6. These guys will be contracted with these guys, for example, and the combinatorics factors are exactly as we did over here, and that will give us a 4 factorial, which will cancel one of the 4 factorials, and then the remaining guys will be contracted with this, okay, and likewise there will be a 4 factorial that will cancel out the other 4 factorial. But I can also contract this set with this set, and then this set with this set. Okay. And so what you discover is that, I believe, all these factors will cancel out, minus I lambda squared. And then we will just get the propagators. So I will get the product of all the external propagators, I over K1 squared minus M squared plus I epsilon, all the way to I over K4 squared, sorry, K6 squared minus M squared plus I epsilon. And then I have now an internal propagator, which is I over P squared minus M squared plus I epsilon. Sorry, I'm out of time, I think. Right, yeah, so, and then let me just finish by saying that, remember there are two delta functions here, right? So this will be, in fact, delta function of this guy, P minus K4 minus K5 minus K6, and then also this guy, 2 pi d of P plus K1 plus K2 plus K3, and then now I have to integrate over P. Okay? So I have to integrate over P, and then you have to choose what the end result will be, and basically we just tell you that P is not any old thing, but P is actually either equals to K4 plus K5 plus K6, or it is equal to negative K1 minus K2 minus K3. But either way, this whole thing will go away. The two delta functions will integrate into one delta function, which will just be the overall conserving one. Del K1 plus K2 all the way to K6. So again, you don't even need to write this down. Once you get used to it, you don't have to even write this down anymore. You just write down the calculators, this one, everybody, and then this is I over P squared, but P squared, P itself, is either the sum of these guys or the negative sum of these guys. And you just write it down like that. And then the only thing you need to figure out, once you get used to it, is just what's the combinatorics factor here. You just have to count how many contractions there are. And in this case, I claim it will just be the coupling constant squared. That's all. Yeah. So once you get used to it, the rules are actually easy to implement. It's just how you got there, right? It's how you got there. There's a lot of formalism involved, and that's the part that's conceptually and technically very, very heavy. Yeah. Okay, so we've done the momentum space transformation of the endpoint function. So tomorrow, I'm going to tell you how are all these related to the scattering amplitude itself. Okay, so see you guys tomorrow.